Right, so we're going to do module 1 and 2 questions. I'm going to start with module 2, standard deviation, because we hadn't done any question regarding to accuracy and precision. All right, I made up 4 points. If you want it, send me the email. I just put in some stuff that you need to know for the exam, so like the procedures for gravimetry, uses, sources of error, that sort of stuff. The method for calibrating a pipette, making a standard solution. So apart from the calculations, no, send
Recording
so apart from the calculations aspect, so even for topics like gravimetry, they can ask you for the procedure, the uses, state the function of the different apparatus. So they can get a proper question that worth a lot of marks in terms of calculation. They can also get the theory part. Yes, I didn't get to send out any emails since yesterday, but I'm going to do it after class because tomorrow is the exam, so yeah, I have to send it. All right. Right, so we're going to start off with, it's a 2011 course paper with accuracy and precision.
Sir,
Yes,
is that under uncertainty?
yes, uncertainty in measurements. Yeah, that's the beginning. And so for this one, you should know how to calculate the pipette and the burette. They might ask it, it doesn't have to come, but just know it. All right, so this question, it starts by asking us to differentiate between accuracy and precision. Now I'm just going to do a quick demonstration again. I am going to do calculations as well. So just to do a quick demonstration of accuracy and precision, if you are to hit the target, this is the target. None of the, so the dots represents the person trying to hit the target. The points are not close to the target, so it cannot be accurate. If it was accurate, this is the target, so the points would be hitting the target, right? That is accurate. If the points are out here, right? So let's compare the two. Let's do a next one. All right. So if you're trying to hit the target, right? None of these points are close to the target, so it is not accurate, right? It must be extremely close to your target. So because it's not close, it's not accurate. The points are not close to each other, so they are not precise. For precision, the set of measured values must be close to each other. If you look here, the points are in a cluster, so they are precise. So precision is how close a set of data values are to each other. So in this case, you have a cluster, so it's precise. However, they are not close to the target, so it is still not accurate. They are precise, but they are not close to the target, so it's not accurate. For these points here, they are close to each other, right? That makes them precise. They are close to each other, that makes them precise. And they are hitting the target, so that makes it accurate. You won't be using this diagram for the exam, you'll probably get some numbers. The point is, for accuracy, you will have a true value. So for example, a pipette, it is supposed to deliver 25 mils. So if you are calibrating the pipette, the pipette should be delivering volumes extremely close or exactly to 25 mil. If you are getting volumes of 24 and 24.5, that is not accurate. So accuracy is how close your measured value is to the true value. That's for accuracy. Precision is how close they are to each other. All right, so the first question, it asks us about precision and accuracy.
Good afternoon, Mr. Hare.
Good afternoon.
So, with the example you gave with the numbers,
Right.
let's say the numbers are close to the true value and they're also precise. Could you say that they're both precise and accurate, or you just say they're accurate?
No, man, you can have, that is why I use this right here. It can be both precise and accurate. The past paper is 2011. Right, so it can be precise and accurate. It can be precise but not accurate. It can be accurate but not precise. Or it can be neither. All right. So
Okay, thanks.
right. So in this case, the points are not close to each other, so it's not precise. It is not close to the target, so it's not accurate. Neither accurate nor precise. For these blue ones here, they are close to each other, so it's precise, but it's not close to the target, so it's not accurate. These points here are clustered and on the target, so they are accurate and precise. These 4 points here, they are not close to each other, so they are not precise. However, they are close to the target, and so it's accurate. All right. So let us just get quickly into calculating standard deviation. Before the standard deviation, it says to list 3 pieces of apparatus that could be used to accurately measure the required volume. So a student was asked to measure 50 cm cube. When I want to measure volume with accuracy, the instruments that we use are the pipette, burette, volumetric flask, and measuring cylinder.
Can you repeat the question, please?
Sure. So the question is, a student was asked to measure 50 cm cube of a liquid in order to carry out an experiment. Remember to mute your mic. So a student was asked to determine 50 cm cube of a liquid in order to carry out an experiment. So these 3 pieces of apparatus that could be used to accurately measure the required volume. So these are the apparatus, these are the options, but if it asks how much again, 3 piece, this will be your last option. The pipette is the first option. It's pipette, burette, volumetric flask, measuring cylinder.
Sir, is syringe can I use as well?
No, you only use this syringe.
In terms of accuracy and precision, that we're talking, but not in terms of the question itself.
Yeah. Yeah, man, continue. What was the question? All right, so Norman, so the analytical balance that is for mass, we were referring to volume. So if it was in terms of mass, then the analytical balance would be used. Okay. All right, so I'm going to put a table on the board. All right. So the student, and we have 4 students. 1, 2. I'm about to mute your mic. All right, so for this question, so we did an experiment, right? So let us continue. So it says, each of 4 students carried out an experiment to determine the percentage of acetic acid in a vinegar sample. The procedure was repeated 4 times by each student, and the results recorded in table 2. So this is the result. Then it says complete table 2 by calculating the standard deviation of each of the 4 sets. So we're to calculate the standard deviation of each student. Student 1, 2, 3, 4. It's just 2 marks. I don't know where they just gave 2 marks of this one. All right, so remember for standard deviation, it's the sum. So it's the sum of x minus x bar squared divided by n minus 1. X refers to each individual numbers. So x is each individual number. X bar, that's the mean. N is the number of data points. So we have 1, 2, 3, 4, data points.
Sorry, can you repeat that, please?
So X is the individual data points. X bar, that's the mean. N is the number of data or the number of trials. So 1, 2, 3, 4 trials. So N is 4. So let us work the first one. So for student 1, it's 24.15. It's 24.15. And the mean for the first row is 24.13. So it's X minus X bar squared. So you must square it. All right, so it's X minus the mean squared. So that would be 24.15, take away 24.13. The answer you get, you square it. Let's square it. All right, and the answer is 0.0004. So you will have to do what we just did for the rest of these 3 numbers, then add them up. All right, and you will have to be.
Sir.
Yes.
Sir, the 24 point.
15.
Sir, you're using the formula, this formula.
So hold on, you see this formula here? You're not just
Yes,
going to,
sir.
you're not going to use it immediately. It says this symbol here that kind of looks like an E, it means this, it means the sum of. So we are working on here, you must have the sum of X minus X bar. So we did the first one, X minus X bar. That's the X, this value here, minus the mean, and we subtract them, square it, we get our answer. But that is just for one individual data point. You have to do it for this one, and this one. Then you add it up. That is what the sum of X minus X bar squared means. So we did one already, and we get 0.0004. So you have to do this one now, and this one, and this one. So there are a lot of us here. So somebody can take student 2, student 3, student 4, and work quickly. For the exam, you have to practice. I'm not going to work the answer. All right, so let's just do quickly. So the first answer, 0.004. Somebody, let us do this one. So it would be 24.20. Take away the mean again, which is 24.13. So for
Repeat,
this one, it's 0.0049.
So you can repeat from after you find the sum of
Repeat the question
what
now.
else you supposed to do?
No, you're sounding a bit low. Can you repeat the question?
After you find the standard, the sum of
Hold on.
the 24.15 and that one, what else you do after that?
Start again. Let me see if we can hear good.
After you find
All right.
the sum of
Sorry, but
between the
I'm going to have
volume,
to exit and come back. A call came in, so the volume on this it dropped. So I'm just going to exit and come back. Because I won't hear you properly. All right, you can go ahead with the question now.
All right, sir. So after you find the sum between the volume 1 and the mean, what else is supposed to do after you do that? You're gonna use volume 2, find the sum for volume 2.
Right, so you're doing volume 1, volume 2, volume 3, volume 4. When you get the answer, you're going to add up all of them. And that is what is going here. So look, I did volume 1 and I got 0.0004. Then I did volume 2 and I got 0.0049. So I need to do volume 3 and 4. When I do volume 3 and 4, this here means I am supposed to add up all 4 of them. So I have just done 2 already. So before I can add them up, I need to find 3 and 4.
Sir, could you feedback your screen?
Oh, all right.
So probably to make it more easier for us, probably you could have write out it the long way to make everybody more get it.
All right. No problem.
Sir, I got
All of this
2.58 for
stuff.
student number 4.
Look back on the table. Just a second. The person that said look back on the table. What about the table? What about the table? All right, so just everybody have the table? I can erase
Yes,
some of
sir.
the, all right.
Yes, sir.
Sir,
No, sir. 1 second, please.
All right,
excuse me, sir.
yes.
Sir, for volume 2, another 24.20 minus 24.13.
Repeat that?
For volume 2 is not 24.20 minus 24.13.
Yes.
But I
And
got
then,
0.07.
and then you square it.
Oh.
Yeah. All right, so let us just, let me go a little slower. All right. I was kind of rushing. All right, so let's just slow it down. All right, so the formula for standard and there's a next column. After this column, you should have a next column that asks you to
That's
put in the
the
standard.
answer there. Yeah.
Right. So there's a next column and it's empty, so you're supposed to put in the standard deviation. So the formula for standard deviation, square root, that sign, x minus x bar squared divided by n minus 1. This symbol here, it means the sum of, all right? So x minus x bar, you are going to work out that for each of these trials, then you add them up. So the first one, x is each individual polynomial. So this is 1 experiment, 2, 3, 4 experiment. So student 1, experiment 1. So it's 24.15 minus the mean, which is 24.13. When you get the answer, you're going to square it. So this is x minus the mean, which is x bar. So when we did this, we got 0.0004. 0.004. So I'm going to put the numbers here. 0.0004. That was the first one. I don't remember what I got for the second one, so let us work it again. Are we okay with this one now? Just to check before we move on.
Sir, how about the N?
How about the end? All
Yes,
right,
sir.
so, right, we are not, you see, so this formula, we are not ready to apply it yet. We are going to apply this formula in the final stage of the calculation. What we are doing is getting the answer for x minus x bar for each of these. When we have the answer for each of them, then we're going to add it up. That is what this is telling us to do. Add up the answers that you get when you subtract the mean from each individual data. So we have the table with the individual data and we have the mean. The formula is telling us that we should subtract the mean from each individual data. When you get the answers for all individual data, we are going to add them up. So we have the answer for the first data here, volume 1. We're going to do it for volume 2 now, and it's the same calculation. The mean from the data. So 24.20 take away 24.13. Remember, when you get the answer, you must square it. And so we get 0.0049. So this is the answer for the second one. We're going to do the same thing for the third one, x minus the mean. So 24.10 take away 24.13. Whatever answer you get, you're going to square it. And our answer is 0.0009. All right? And then you go to the final one now. 24.05 take away 24.13. Whatever answer you get, you square it. Remember, if you get a negative number, when you square it, it's going to give you a positive number. Yes, it's a lot of working out for 2 marks. Still can get that over, but yeah. So 0.0064 is our answer. So now we have done x minus x bar squared for each of the 4 experiments. So now we're going to add them up. So it's 0.0004 plus 0.0049 plus 0.0009 plus 0.0064. And the answer I'm getting is 0.0126. All right. So the sum of x minus x bar squared is 0.0126. Remember now, n is the amount of trials.
Sir,
Yes.
could you repeat how you got that value?
Which one? This one?
Yes, sir.
So after we work on each of them, we reach the part of the formula now where we are adding up each of them. So remember, this symbol is telling us to add up each of these answers we get. So we have our 4 answers, so we are adding them up. All right, and so we get 0.0126. So you see on this side of the board, this is what the sum of x minus x bar squared, this is what it means. You work out x minus x bar for each of them, then you add them up.
Sir,
Yes?
When you did the first value, you did 24.15
Yes,
and minus 24.13.
that is
I
correct.
can square it. So when you insert that in the calculator and you square root it, so the
Okay,
n
okay,
minus one.
just a second. When you get the 0.004, that is
Mm-hmm.
where you stop. You stop there. Do not square root it.
Okay.
Right?
Okay.
Move on and do the next one. And that is
Oh,
how right. And you get the second answer. Then and you do the third one, you get the answer. You do the fourth one, and you get the answer. So when you have completed all of them, you are going to
mhm. Okay.
yes,
Okay.
so yes, so let me just move this. Let me just move this in one and put add up. So that is what it means. We are going to add up x minus x bar squared. So we get x, so this is one answer, this is two, this is three, this is four. We're going to add up the four of them. When you add up the four of them, we get this answer. And
Then
then
divide it by
we're
3.
supposed to divide it by n minus one. N is the amount of trials. And we did 1, 2, 3, 4. So 4 take away 1 is 3. All right. And so 0.0126 divided by 3, we get 0.004.
3.
Please repeat.
3.
Yes, we remember n is the amount of trials, and we need 4 trials, so 4 take away 1 is 3,
Oh, okay.
right? So we're going to divide it by 3, and then the answer we get, remember, we have to square root it. So it's actually the final answer that we're going to square root. And so when we divide this answer here, I'm going to get 0.0042. When I square root that answer, I'm getting, so the final answer is 0.065. So the standard deviation for student number 1 is 0.065.
Sir,
Yes,
seeing that the values in the table had 2 decimal places, I left mine at 0.06. Is that okay?
yes, it would, yeah. Because yes, you should work with the two, stick with whatever unit is in your table, just stick with it. So 0.06. All right. So can you try? All right. So just quickly, just calculate number 2 and tell me your answer.
I got 1.15.
1.15. Let me see. Yes, 1.15 is correct. Did anybody try number 3?
Sir, the mean value for student 2 is 26.00.
The mean? No, 25.
I got 3.46 for number
Oh,
3.
wait, sorry. Yeah, no man. It's the mean for student 2 is 25. Sorry, will this be? Yes, I'm going to upload it after class. Right, so did anybody get an answer for number 3.46, right?
So, sir, we're going to find the mean value for all the students.
No man, they gave us the mean already.
Not the
No,
mean value, the standard deviation for all students.
right, that is correct. No, if they did not give you the mean, the first calculation that you would have to do is to calculate the mean.
And the mean will be like the average of the 4 values.
That is correct. The mean is the average.
Sir, I just wait, but the other is like when I type it in my calculator, I'm getting like a fraction. I don't know how to fix it.
Press SD. Look for a button. Look for a button close to the
Yeah,
top.
the S.
Yeah, press SD.
Yes, sir. I pressed it, but like when I calculating, like for instance, for student one, volume one, like I said, 24.1, open bracket 24.1 minus the 24.13, close bracket. They square at same time, right?
And what again?
I'm getting the fraction.
And you
And when
press,
I press SD, it's not working. But when I don't square it and I press SD, it's working.
all right, don't, hold on. You mean when I don't put it in the bracket?
Yes, sir.
All right. So do it that way then. All right. And what was the answer for number 4?
2.58.
All right. So after we completed the table, all right, let me just put the answers on the board. So the first answer was 0.06. That was for student 1. Then 1.15. That was for student 2. Then 3.46. That was for student 3. And then 0.08. That was for student 4.
So, sir, about
Yeah.
15 marks is work.
I'm actually seeing 2 marks, honestly, on the paper.
Man.
Eh?
They're up with
No, how they put 2 marks to this, honestly.
Sir,
Yeah.
sir, what's the value for in student 1, volume 1?
This 24.215.
No, student 2, student 2. The values I have to decide start at 0.06.
Hold on. Which value one?
So the values that you were calculating for student 2, the volumes.
For student 2, it was
So
26.
on your, it's on my right. So the value there you have 0.06, 1.15.
Oh, these are the answers. Oh, so 0.06 for student 1,
Sir, the
1.2.
one for number 4 is incorrect.
No, it's not.
It's 2.58.
You made a mistake. All right.
Sir, 25.10 subtract 25. When you square that, you get 0.01.
Well done. Take time. So repeat the answer. So for number 4,
25.10 subtract 25 give us 0.01. When you square it, 24.90 subtract 25 give 0.01 when you square it, and then 25 subtract 25 is 0, and 25 subtract 25 is 0. So you have 0.02 over 4 minus 1, that is 0.02 divided by 3. That gives you 6.66. And when you find the square root of that is 2.58.
all right, so let's go again. So
Unless my values are incorrect. Oh, the mean is not 25. Okay. All right, thanks.
For this, for number 4,
Yeah.
yeah, the mean is 25 for number 4.
25.
Oh, so
But
if
when
it's 25, then I'm correct.
All right, let me
a
check it out.
0.08, me get 2, like sir. So after you get the 0.006, you're supposed to square it, find the square root of it.
Did you
0.077.
find the square root?
Yes, I found the square. Yeah.
All right, so let's go on. All right, let's do number 3. Is anybody else get a different answer for number 4 other than 0.08?
No, sir, I got 0.08.
All right, what was the answer for number 4? When you did 25.1, what was the answer of that?
I got 0.1, and then when I square it, I get 0.01.
But sir, look at the values for student 1 and student 4. They are almost similar. So the SD value for number for student 4 couldn't be 3 point something. That would be too large.
Number 3 is 3 point something. This is student 1. This is student 2, student 3, and 4.
Okay.
Can I work out all of them on the board, please?
All right, so number 4, let's start with number 4. It was 25.10, then 24.9, then 25, 25, 25. All right, so 24.1, no, 25.1, take away 25, square it, you get the 0.01. 24.9 take away 25, the square that, you get 0.01.
And then the rest would be 0.
This would be 0. All right, so 0.01 that's divided by 3. And you get 0.08.
So it's 0.006. Oh, my calculator is not in standard form. I'm sorry about that.
All right. You did remember to, when you add it up, you did remember to divide it by 3.
Yeah, I divided it by 3, but I got 6.60, but I didn't realize that it said times 10 to the negative.
Oh, yeah, standard form.
So I never
Right.
It's not recommended by doctors, but people use it and
All right,
find what's done.
Sir, you
This
know
is
to change your calculator out of
Yes,
standard
sir, you know
form.
how to change it, calculator to standard form. This is our Casio.
Casio. Look at the top if you have mode on it. Look at the
Yes.
top if you have mode. Press mode 3 times.
Repeat, sir.
Press mode 3 times.
1, 2.
Oh, okay.
It's like it absorb.
Do it quickly and tell me what I say on the screen.
Fixed iron norm.
Press 3.
Okay. Norm 1, 2, question sign.
Press 2.
Okay.
But
You
me
see
I press mode
it's
and
in the
I see
normal
a
mode
thing,
now,
yes.
alright? Alright, so just
Sir,
mute. Yes? Go
sir,
ahead.
the calculator should be in standard form and not degrees.
No man, degrees is something else. For standard form is when you get the large numbers and you don't want to be have to interact 0.00 whatever, you just switch it to standard.
Oh,
Yeah,
that the times 10 to the minus.
right. So you can easily just press mode 3 times and you will see SCI. SCI is if you want it in scientific notation, or if you want it like 0.00, you press NORM. Okay. So it's 2 for this and 3 for this. That's it. All right, so this question is taking a long time. So let us do number 3 now. All right, so number 3, it would be 29.15. Take away 28.78, which is the mean. So I'm getting 0. Now square it. When I square it, I get 0.1369. That's for the 29.15. Then 24.95 plus, not plus, minus 28.78 squared. Let that go again. 24.95 minus right 14.67. That's for the 24.95, and then 33.25. $19.98. And for this one, 1.06.
Sir,
Yes.
sir, for the top value you have 0.1369. Shouldn't that be in 2 decimal place?
Yes, well, I think I square root this. Give me a second. Let me give up to see if I did square
No,
root.
sir, it is correct. You know, we're just saying why you didn't put it to 2 decimal place. Like
No,
we
I
have
don't
the
know.
others.
That would be 1.4. All right, so let's add them up now. So 0.14 plus 14.67 plus 19.98 plus 1.06. So I'm getting 35.85. All right. And I'm going to divide it by 3, and I get 11.95. So the square root of 11.95 is 3.46. Right? So the value for this third row is 3.46. So let me put back the answers on the board again. So for student 1, it was 0.06, then 1.15, 3.46, and 0.08. All right, so this is student 1, 2, 3, and 4. All right, so that said, each of the 4 students carried out an experiment to determine the percentage of acetic acid in vinegar. Procedure was repeated 4 times, and we have the values below. So for student 1, all right, so based on these readings, it says evaluate the results obtained by each student by commenting on the accuracy and precision of each set of titer volumes. So for student 1, let us comment on the accuracy and precision of each set of values. The standard deviation, it gives you an indication of the accuracy, not the accuracy, the precision. If you have a high standard deviation, it means that the data from one child to the next are not close. They are far apart. If you have a small standard deviation, your results are precise. All right? So let us look at the precision first.
Sorry, what did you say the standard deviation does?
It gives you an idea of the precision. So if you have a small standard deviation, it means that the value from one child to the next are close. Now, if you have a large standard deviation, it means your answer is far apart from one child to the next one. So in terms of accuracy, student number 1, is the standard deviation small? If it's below 0.1, that is good, right? So would you say student number 1 answer is precise?
Yes, it is
Yes.
precise.
Yes, sir. Yes,
All
it
right.
is.
Look at student number 2 answer. Would you say it is precise?
No, sir.
No, sir.
Student number 3.
No,
would you say
sir.
it is
No,
precise?
sir.
All right. And student number 4.
Yeah,
Yes,
man.
Yes,
sir.
sir.
Yes.
Right. So 1 and 4, those are precise. Now for accuracy, it's supposed to be the closeness of the data to a true value. So I was looking for these measurements, what was the true value it is supposed to be close to. So for part B in the question, it had said a student was asked to measure 50 cm of a liquid in order to carry out an experiment. List 3 apparatus. And then for part C, each of the students carried out an experiment to determine the percentage of acetic acid. The procedure was repeated 4 times by each student. But complete the table, get the standard deviation. All right.
So you
So
speak about the accuracy part as it?
no, it I'm looking at. So accuracy, yes, go
I'm
ahead.
saying you would use the mean to be the true value.
That is what I'm going to look at. So, but remember, you'd have to compare each student. So for student 1, their mean is 24. For student 2, it is 25. For student 3, it is 28.78. And for student 4, it is 25. So if we are looking at the mean as a true value. Remember, all of them are doing the same experiment. One took 24, next one took 25, next one took 25, and the other one took 28. So based on this, we could assume that the 25 cm cube is the true value for the, so we're trying to determine the percentage of acetic acid, and based on the mean, we're getting 24 from one set of data, 25, 28.78, and 25. Now the question did not tell us the true value for us to compare it to. So if we're comparing them to the mean in terms of accuracy, we would use tables 2 and 4, which is the 25. Now 28 is way off based on that. So in table 2 and 4, the average or the mean is 25. So if we're taking 25 as the true value, what relevance does the 50 mil have then? Exactly, it don't have any. Because these readings, the average, they are supposed to be getting 25. That is why I was looking for something to compare it to. Because if the student was asked to measure 50 mil, it doesn't have anything to do with this experiment in part C.
Sir, I'm not sure about what my teacher did. For each student, she just compared separately. So the mean, if for student 1 it is 24.13, she compare all the volume with the 24.13. And then she do it for number 2. For student 2, she compare everything to 25.
She compared the individual data to the average.
Yeah.
Right, so if we did that, 24.05, 24.1, 24.2, 24.15, so 24.13, that is.
But that still wouldn't be accurate.
No,
then
it's not
26 to
accurate.
25. But if that is the only one we could say would be accurate was number 4. If we use that one. So the only one that would be accurate. So if you look at number 4, those set of answers are close to the mean, which is 25. If you look at number 3, it's not close. Number 2, 26, 24, 24, 25.
It is off by 1.
That's not close. Yes, that's actually off by 1. But in trial 4, it's off by 0.1. I notice trial 3 and 4 is exactly as the same. So the only one that we would see as accurate would be number 4, because the rest of them are off.
I'm not sure if
Our students are doing the same thing. Right, all of them are doing the same experiment.
Are we on the question that's on the board?
Please repeat.
We're looking at the values that are on the board.
Right, so after we have calculated our standard deviation, we are supposed, so the second part of the question, it says evaluate the results obtained by each student by commenting on the accuracy and precision of each set of volumes. So, yes, go ahead.
Sir, I would say that student 4 answer is accurate. Student 1 answer is precise, but student 2 and 3 answers are neither accurate nor precise.
Student 1 is precise but not accurate. Student 4 is both accurate and precise.
And 2 and 3 is neither not accurate nor precise.
Recording it. Right, 3 is neither of them. So 4 is both accurate and precise. So let me just remind you, we're using the standard deviation to comment on the precision. Once it is small, they are precise. And for small, we are using a value less than 0.1. And in this case, these two are extremely small, so they are precise. So we had already said that 1 and 4 is precise, and 2 and 3 are not. So then now we were comparing the accuracy of it. So for number 4, we would definitely say that is accurate. Number 2 and 3, these numbers are a little far from the mean, right? So that is what we would do. So 4 is accurate and precise. Number 3 is neither accurate nor precise. Are we following?
Yeah, man,
So
sir.
it's
Sir, what values are you using, sir?
Please repeat.
What values are you using when it said 1, 2? Because I just joined. I'm kind of confused.
Oh, so we had calculated the standard deviation for each of the students. We're doing number 2 from 2011, and it's on accuracy and precision.
Okay, thank you.
In measurements. Are we going by column or row? No, we are going by, so for student 1, it's the first row. And we calculated the standard deviation to be 0.06. Then student 2 is the second row, standard deviation 1.15. Student 3, third row, standard deviation 3.46. And the fourth student, standard deviation of this. And then now, after we have calculated it, we need to comment on the accuracy and precision. A small standard deviation means it is precise. So student 1 and 4 precise, students 2 and 3 is not. Then we have to comment on the accuracy. And then so if we comparing the individual data to the mean, student 4 is very close to the mean. So we would say student 4 is accurate. And we had already said it was precise. So for student 4, it is accurate and precise. For student 1, we had said it was precise, but it is not accurate. So for student 1, it's precise and not accurate. And for 2 and 3, we are saying it is neither accurate nor precise. Why isn't 2 precise? So again, for precision, we are using the standard deviation value. So standard deviation, it basically tells you how close the set of points are. Why isn't 1 accurate? It's not close enough. The answers are not close enough to the mean.
so once the answers are close to the mean, they're accurate.
Right.
Okay.
Why isn't 2 accurate?
Because of standard deviation.
All right, for number 2, the mean is 25. And the first volume is 26. The second one is 24. Third is 24. Fourth is 26. And the mean is 25. That wouldn't be close enough to be considered 25. I saw somewhere where they had said number 2 is accurate, but I wouldn't agree with it.
Excuse me, sir.
Yes.
Are comparing the mean for student 1, all the volumes?
Right.
So, sir, look there, you have 24.15 on the board I'm talking. You have 24.20, you have 24.10, and you have 24. All of them is 24. They look pretty close to me.
2.13, 24.15. Oh. They're actually, yes, 24.15, 0.20. Can't disagree with that. All right, we're going to work with this one, but when I upload it. I'm going to put in the description the answers again. I'm going to get some other perspective on this one. All right.
Sir, question.
Really ago.
You said 2 would be accurate and not precise?
For number 2?
Yeah.
No, we had said it wasn't accurate or precise.
But isn't the mean 25, sir?
Yeah. And the values 26, 24, 24, and 26. Isn't 0.1 considered precise? No, it's the...
Yeah, sir.
Hmm?
I see what you're saying.
All right, but I'm going to, this question kind of off, but so I'm going to check with other persons and post the answer, a final answer in the description. However, the only thing we're querying here is the accuracy. The precision, once you get your standard deviation, just look at the value. If it is extremely small, so we may have 1.1, no, that's big for accurate, for precision. All right, so we're not even wondering what is precise or not. We're sure of the precision. 1 and 4 is precise, and 2 and 3 is not. All right, so we're sure about the precision. We're just deliberating the accuracy. All right, but the precision, we're certain about that point. All right. So part D. Wait, we're here from about 4:30, 1 hour. All right. So for the calibration of the pipette, it said a student was asked to calibrate a 10 cm3 pipette, outline the steps that should be taken by the student to complete this exercise. All right, so quickly, let me write it on the board. So what you would have to do, right? You would have to first put some distilled water in a container to get to room temperature. So that's the first step. All right, just write this down to save time. All right, so you pour some water in a, let's say, hold on, it's a 10 ml pipette. All right, so we can use a 250 ml beaker, right? You just pour some water in the 250 ml beaker and let it stay for about 10 to 15 minutes. All right. So you just pour the water, let it stay for about 10 to 15 minutes, and then you record the temperature. So you do that first.
So you mind repeating?
Yeah, repeat
So you pour some, all right, just fill a 250 ml beaker in, sorry, I was reading a message. Fill a 250 ml beaker with water. All right, let me just write it.
So which question is that?
It's same 2011. So part D, a student who was asked to calibrate a 10 ml pipette. The marker is sticking to the board.
Weigh the beaker.
Yes, sir. Would you weigh the beaker?
That is correct. So, all right, so you pour the water in the empty beaker, allow it to stay for 10 to 15 minutes, then you record the temperature. That's for one of the beaker. You would get a next empty beaker and record the mass of it. All right, so you just get a second beaker and record the mass of the beaker.
Sir, or you could have just record the mass before actually pouring distilled water.
No man, that beaker with the
water.
is not the one we're
Yeah,
going to weigh. All right, so you get a new beaker. So one beaker with the water. So you should have one beaker with the water. Then you're getting a new empty beaker, right? And you're going to weigh the mass of the empty beaker.
250 ml oxygen.
Sir, should we ensure that it holds the same amount of water as the one that we actually have with the water?
No. Remember, it's a 10 ml pipette. So we only put in 10 ml of water in it. So you just want a container with your water that you are going to be taking from each time. So you just fill the beaker with the water, let it stay for 10 minutes or so, get the next container, right? You're going to record the mass of the container. Once you
Also,
record the mass
sir,
of,
this
yes?
question is related to our accuracy and precision lab.
Yeah, man.
Oh,
So it's
okay, no, I
calibration of
understand.
it's calibration of the pipette. So once you record the mass of the beaker, that is when now you're going to use your 10 ml pipette to transfer 10 ml of water into the beaker and record the mass again. So you should have.
So that beaker is basically to refill the pipette every time it finishes?
That is correct. So one beaker with the water, right? That you're going to be pipetting from each time. And then you have a second beaker that you are using to weigh the mass of the water. So it's empty beaker, so mass of empty beaker, mass of empty beaker, and then beaker, mass of beaker with water.
So one is to pour the water and one is to collect the water.
Right.
So say after you pipette it, then you weigh it.
That is correct. So you're going to weigh the empty beaker, then you're going to transfer 10 ml of water to the beaker, and you record the mass of it. Good? And then you're going to pour out the water, dry it, and do it over and over again. So probably do it 5 times, 10 times, that's it. But it's a really simple experiment. So again, all you do, you don't have to be a beaker, whichever. All right, so going back over, right? It doesn't matter which container you choose. So if you want to choose a conical flask to hold the water, just choose a container, all right? So step 1, just pick a container out of the lab, right? I chose a beaker. So it's a 10 ml pipette. I'm saying get a 250 ml beaker, fill it with water, all right? And allow it to stay at room temperature for about 10 to 15 minutes. I remember students from my class, you have the PowerPoint with these steps already. So the procedure is in there. And if you want the PowerPoint, again, I told you to send me an email. All right, so the first step, you have the beaker with the water, or whichever container you choose. Then you get the next container, you weigh it, all right? You weigh the empty container. So step 2 is weighing the empty container. Step 1 is just adding the water to the empty container and recording the temperature of it after 15 or 10 minutes. Step 2, you weigh the empty beaker. Step 3 is when you're going to transfer the water to the beaker using your 10 ml pipette. All right? And once you transfer the water to the beaker, you record the mass of it, and that's the log. All you're going to do is repeat it 5, 10 times, all right? Any amount you choose. Fill a container with water, let it stay a little, record the temperature. Get an empty beaker, pipette your 10 ml of water inside of it, weigh the mass. experiment finished.
The air must have a RMM.
Were you asking a question? Alright. So that is for calibrating the pipette. Alright. If it's 25 mil, it's the same thing. Alright, why do we calculate the temperature? Alright, so the calculation, we're going to have, so where do we record the temperature? Alright, so remember, the pipette is used to record volume, but we did not record the volume of the water. We are recording the mass of the water. So if you had done the experiment, you would have constructed a table, right? You would have constructed a table, and a part of the table, you would have mass of water. And to get the mass of water, you would have subtracted, so it would have been mass of beaker and water minus the empty beaker. All right. Right, so if you want the mass of the water, it will be the mass of the water and the beaker minus the mass of the empty beaker. So from doing the experiment, you would have calculated mass of water. To get the volume of water now, you are going to use the formula. So mass is equal to density over volume, right? So if you want the volume, sorry, what am I writing? Density is mass over volume, right? So if you want the volume is mass over density. So the reason why we use the temperature now, water has a different density at particular temperatures. So the temperature is to give us the density of the water. So at 27 degrees Celsius, water has a different density from 27.5, 28, 26. All right. So the purpose of recording the temperature is so that we can get the density of the water and transpose the formula. So volume is mass over density. You would have gotten the mass from the experiment, and now that you know the density, you just put volume is mass over density. All right. So quickly, let us say you for mass, you got 9.8, 10.1, 9.9, 9.7, and 10. All right, that would have been the mass. Let us say the temperature of the water, it was 27 degrees Celsius. And at 27 degrees Celsius, the density was 0.00074. All right. The volume of 10 grams of water, would be 10 divided by 0.0074. All right. Let me just write it quickly. 10 divided by 0.00. Oh, I put 3 zeros. 0.00074. I would have gotten 13.5. That means it was 20. I don't remember exactly. I'm just making up a number here. So 10 divided by 0.0074. And that was What is just making up a number, so it will be off. So I would have gotten 13, so 10 divided by 0.00074. I would have gotten 13 point, which 13,000. Density is mass over volume, volume is mass over density. Give me a second, I want to show you an accurate calculation. Just 1 second. Let me just Google it quickly. Density. Just a second. All right, so 20 degrees Celsius density. All right, so 10 degrees Celsius, the density is 0.7979. So let us try about that. 10 divided by 0.7979, we got 12.5. All right. So the volume of water would be 12.5 milliliter. So if you happen to get this on the exam and they give you the mass, they would give you the density as well. And you're going to divide each mass by that density to get the volume of the water. And then you'd have to find the average and then subtract each individual from the average and plug it into your standard deviation formula, just like we did here. All right. So we need to do some more calculations. There's thermometric titration as well. Do you know the procedure for thermometric titration?
No, sir.
Yes, sir.
All right. So in thermometric titration, so remember, we have different types of titration with acid base and redox. We're looking for a color change. In thermometric titration, if it comes, it might come because it is a graph and we'll have to cut a graph. So with thermometric titration, we're going to use temperature readings to determine the endpoint of the titration.
Excuse me, sir, before you move on, how do you know when the pipette is finished being calibrated?
No, that is it. You know, all you're doing is see once you take up the volume of water in the pipette and place it in the beaker and weigh it, that is where the procedure ends. All you're going to do now is take more than one readings of it.
So, sorry, would I already have the 10 centimeter mark on it, or is it?
It has to have it. So when we say 10 mil pipette, it's supposed to deliver 10 mil. So that is why we have 10 mil, 20 mil, and 25 mil pipette.
Okay. Basically, we're just proving it.
Exactly. So you want to see
okay, no problem.
Right. So you want to see if the 10 mil pipette actually delivers 10 mil. Right.
Yes, sir.
Sir, our thermometric titration, didn't you say we use temperature readings to show our neutralization point?
That is correct. So in acid base and Redox titration, we're looking for a color change. But in thermometric titration, we're going to get temperature reading. So remember, acid-base titration, it's an exothermic reaction, all right? So because it's an exothermic reaction, heat is going to be generated. So for example, let's say, yes?
So them can test on the other titrations.
All right, in terms of that one, this syllabus, it don't go into detail, so we don't do experiments and so for it.
Okay.
So if it come, which is, I'm not going to say it cannot come, but if it comes, it would be a graph, all right? So it's for potential metric titration, thermometric, and conductric metric, if I'm pronouncing
Sir,
it right.
I saw one with the thermometric titration. What they did was that they gave us the values for the graph.
Right.
They told us to plot the graph, and then they asked us what was the end point.
So that is what I'm going to show you. So the procedure you really have to know is thermometric, because we actually do that as labs and so forth. So what would happen as a procedure, you would have your conical, not conical flask, because it's an exothermic reaction and you want to minimize heat loss, you are going to use a styrofoam cup, all right? So for thermometric titration, we are not using a conical flask. We are using heat change to determine the neutralization point. So you want to reduce heat loss. So we don't use conical flask. We need a container that can contain the heat. So we would use our styrofoam cup. And you would have your solution of, let's say, the base, sodium hydroxide inside of it. And you're going to
indicator.
No indicator. So that is what I'm saying. We are using
Indicator is for redox, right, sir?
Please repeat.
Indicator would be for redox titration.
Not in most redox reaction.
Like color change.
Right.
Third question though, how would you know when is the end point?
Right. As soon as I'm finished, I'm going to show you. All right. So you will have this styrofoam cup, right, with the base in it. You are going to have a table, right? All right. So this is your burette. Good. Inside of it, you have your hydrochloric acid present. This is your sodium hydroxide. Titration is going to take place. How will this titration take place? So first, before you add any sodium hydroxide, before you add any hydrochloric acid to the beaker, you are going to record the temperature of the beaker, the temperature of the solution. So before you add any HCl, that is 0 cm cube, you are going to record the temperature of the solution. Let us say it is 26 degrees Celsius. Good. So at 0 cm cube, the temperature is 20 cm cube. Then they are going to add 5 cm cube from the burette into the sodium hydroxide solution and use a thermometer to measure the temperature. All right. So you must use a thermometer. So let us say when you add 5 cm cube now, the temperature increased to 27. You add 5 more again and stir. Let us say, so when you add 5 more, that would have been 10 cm cube, and you measure the temperature again. Let us say it go to 28. And you will keep on adding 5 cm cube. All right? If you want to add 1 cm cube, it's up to you. But you are going to choose a specific volume and you are going to add it in that increment each time. So if you want to add 2 cm cube, it's up to you. but you are
Okay,
going to
sir.
add it
So
in a
when the
specific
temperature,
amount.
that mean when the temperature start decrease, that would that be when we stop then?
Exactly. So let us say it increased to, so just a second. So let's say it goes 28, 32, then 31, 31, or 31, 30.5, you can stop, all right? Because you would have gotten the maximum temperature, all right? So the maximum temperature, that is where neutralization occurred, all right?
So,
So in terms
sir,
of, yes?
what happened to this the part where they said that we have to draw 2 lines on the graph?
I don't reach, well on, I don't reach, I am explaining the procedure, then the graph. So in the procedure, you have a styrofoam cup, right? You are going to put either the acid or the base inside of it. Good? Once you put it in there, you record the temperature of the solution. So before you add anything else to the styrofoam cup, you record the temperature. So let us say it is 26 degrees Celsius. It's a titration, so you need to add a solution from the burette to the container. Good? You are going to add the solution from the burette in increments. Let us say we choose to use 5 centimeter cube. Each time you are going to add 5 cm cube, you record the temperature. So you add 5 cm cube, you record the temperature. You add a next 5 cm cube and you record the temperature. You keep on doing that and record the temperature. At the end of it, you will get your temperature readings and the volumes. All right. Now, once you get that reading, you are going to plot a graph of temperature versus volume. And this is how it will look. So we remember in the experiment, the temperature, it would have increased and then it would have decreased. The temperature, it starts at 26 degrees Celsius. If you get a graph to plot and they don't give you a scale, the lowest temperature you get, you are going to have to break the graph because you need to spread out the data. All right? But this is how your graph will look. No.
Sir, what you were saying about breaking graph?
So because the temperature starts at 26, right? So let us say this is 26. You're not going to be like 0, 5, 10, 15, 20. No. You're going to break the graph and start it at 26. So that the data points can make up 75% of the graph. Remember, you get marks for using of the graph paper. If you don't break the graph, your actual readings are going to be in a small area. Good, so you have to break it so that these points can extend out. Right? Now, how do you draw this line? When you draw the line, so you draw 2 lines of best fit. One in this direction and the next one for the points that were decreasing. You see the highest point here, the lines don't have to go through it, but they must intersect either through it or above it, not below it. Remember, the highest point is where neutralization occurs. So you cannot let the 2 lines intersect below the highest point. It can intersect above it or through it, but not below it. All right? Now, when you plot a graph, remember on this axis, you will have the volume of acid or the base, whichever was in the burette. So whatever is in the burette, that is what is plotted on the graph. And you will have the temperature readings on the y-axis. Remember, I said that the calculations, best fit line. So if these are your points, right, you would not do this. That would not be a graph. So you should not connect the dots. The line of best fit, how do we know which goes on the X again? The dependent, so the dependent variable goes on the y-axis, the independent goes on the X. So based on the amount of acid that you're adding, it will change the temperature reading that you're getting. So you don't have any control over the temperature reading. So the temperature you're getting is dependent on the volume of acid you're using. So it's the dependent variable on the y-axis and the independent on the x. However, they will say plot a graph of this versus that. Whichever comes first goes on the y-axis. So if they say plot a graph of temperature versus volume of acid, temperature goes on the y, volume of acid goes on the x-axis.
Sir, question.
Yes.
For the volume of acid, is it the acid that you use out of the burette or that is left in the burette?
No man, what is used from the burette?
Okay.
Right, because remember, it's not like acid-based titration now. So remember, we would have added 5 cm³ first and record the temperature. So when you add 5 cm³, you would record the temperature at 5 cm³. Let us say 27. When you add the next 5 cm³, which would make it 10 cm³, you would record the temperature again. Let us say it's 27.5. And if you add the next 5 cm³, that would be 15, and you record the temperature again. So you would, in your table, you will have a series of volumes and the temperature readings. So you should not connect the dots on your graph. You are drawing 2 lines. One line from this side and one that side. All right? The only thing we need from the graph is where it intersects. We're going to draw a line come down to the y-axis. Because remember, when we do a titration, all we need to do is figure out the endpoint. When we do an acid-base titration, we look for a color change. When we do a redox titration, we look for a color change. When you do thermometric titration, you are going to get a graph. The lines will intersect, all right? Wherever they intersect, you draw a line come down to the x-axis. And that is it. You just read off the volume from the graph. All right? So let us look at, there was a thermometric one, even though the graph is not plotted, we can still attempt it. All right? So let us look at the thermometric one. Where is it? All right, so right. So they gave us some readings, so let me just put the readings on the board so you can see what I was talking about. So and this was 2015, all right? So you have volume of acid, and you have temperature in degrees Celsius, all right? So when you add 5 cm³ of acid, the temperature was 30. When you add 10 cm³, it was 32. When you add 15, it was 32.5. When you add 20, it was 33. When you add 25, it was 34. When you add 30, it was 33.5. When you add 35, it was 33. When you add 40, it was 33 again. And when you add 45, it was also 33. All right, so this question is from 2015. And it says, so in a thermometric titration, 25 cm cube of 2 moles per dm cube sodium hydroxide were used to determine the concentration of hydrochloric acid. Use the table below to plot a graph of temperature versus volume of acid. So it already tells you plot a graph of temperature that will go on the y-axis versus volume on the x-axis. After you plot the graph, it says, hence determine the endpoint volume of the acid. It's 2015. So again, when you plot your graph, I am just going to put the shape and the 33, all right? So this would be your graph. You're not going to start at 0, you're going to start at 30. So you would bring the graph, and your first point is 30. And you could probably go by 0.5. So 30, then 30.5, 31, 31.5.
Sir, what year are you doing now?
Oh, they gave you a scale, right? And you see it break, right? So when you see it start at 30, right? But I'm saying if they did not give you a scale, then you could break the graph and then go. All right, so 32, 33, let's just put 34 up here. All right, now 34 is the highest temperature. So I'm going to put 34 in the middle, right? And then you would have some points going across, right? So I'm not putting it, I'm just putting in some points. Good. And then afterwards, it is going to decrease. Once you get to 34, it's 33.5, then 33, 33, 33. So everything in the same line. Good. And then you do that. All right. That is how the graph will shape. Now, when it says, determine the
Excuse me,
endpoint.
sir.
Yes.
Is it two basic lines?
That is correct.
Okay.
Right, so you draw one for the left-hand side. So the highest temperature, right? You draw one line through it for the left-hand side and the next one for the right-hand side. So it's 2 lines, right? And then now, to get the endpoint volume, that means where the acid and the base neutralize each other, is where the lines intersect. All right. So when you draw the line from here down to the x-axis, let us say at this point, the volume is 22 cm cube. All right. Let us say where the line touches the x-axis, it matches with 22 cm cube. Then the endpoint volume of the acid is 22 cm cube. All right. That is it. So this is the only thing that you need from the graph. When the acid and the base neutralize each other. And that is where it intersects. And you read off the volume. So as I had said before, titration in terms of calculation, nothing is going to change. The only thing that is changing is the procedure for obtaining the endpoint. So we obtain the endpoint a different way in thermometric titration than how we obtain it in acid-base titration. But in terms of calculation, it is the same. All right, so it says outline these experimental steps for this type of titration, and I went through it. All right, no calculation? Anyways, I'm going to do a calculation for
Yeah,
you.
for the acid.
Sir,
Yes. Oh,
2017's paper has
right.
a calculation.
Pull up the window, let me call him. Christian!
All right, so again, I don't understand this. They only gave you 2 marks to calculate the concentration of the acid. But that's how it is.
Sir,
Yes.
in 2017, you have to do a lot more calculations. You could check that out.
You have a next one for 2017?
Yes, sir.
Send it to this email.
Okay.
All right. Yes, send it and I will work it after we do this one. All right, so it says calculate the concentration of the acid. So let us look at the information that was given. Dijon, send it to me next number. All right, so the concentration of the sodium hydroxide. So sodium hydroxide concentration is equal to 2 moles per dm cube, and the volume is equal to 25 cm cube. And if you recall, I told you that in any titration, you have to get concentration and volume for one of the substances. And for the next substance, all you would have gotten was the volume, which case is HCl. And from the example, I had said the volume of HCl was 22 cm cube. And we're going to try and find the concentration. So we have concentration and we have volume of the sodium hydroxide. Therefore, we can calculate the number of moles. So remember, concentration is mole divided by volume. So mole is concentration times volume. So step 1, we're going to calculate the mole of sodium hydroxide. So it's going to be 2 moles per dm cube times 0.025 dm cube. So we're converting the cm cube to dm cube. And remember, 1000 cm cube is equal to 1 dm cube. So 2 times 0.025, we get 0.05 moles. All right. Then step 2. So remember, if we want the concentration of HCl, we already have the volume of HCl. So all we need is the mole of HCl. But we did not get enough information for HCl to get the moles. So what we're doing
So we're
is
going to write the equation now?
that is correct. So we find the mole of sodium hydroxide, then we are going to use the balance equation and the mole ratio to give us the mole of HCl. So when sodium hydroxide Don't leave out the state symbols when you write an equation. So sodium hydroxide reacts with HCl, you will get sodium chloride and water.
No water.
Right? And we know that the mole ratio between sodium hydroxide and HCl is 1:1.
1:1.
Right? So if the mole ratio is 1:1 between sodium hydroxide and HCl, how many moles of HCl do we have?
0.05.
Right? So the mole of HCl is equal to 0.05. So now that we have the mole of the HCl and we have the volume of HCl, we can go ahead now and calculate the molar concentration of HCl. So it is 0.05 mole divided by the volume in bm³ is 0.022 bm³. And you get 2.27 moles per bm³. All right. So that is the concentration of the sodium hydroxide, not sodium hydroxide. This is the molar concentration of the hydrochloric acid solution. Now,
I'm sorry, could you go over that one more time, please?
from step 1 or from where?
From the first calculation.
All right. So we are trying to find the concentration of the HCl solution. It's a titration, so they have to give us the concentration and the volume of one of these substances. All right? So we are using a standard solution, which means the concentration has to be known. So the first calculation I want you to do is to calculate the moles of the substance, which you have both the concentration and the volume for. In this case, it is sodium hydroxide. So you calculate the mole, you get 0.05. We are converting the cm³ to bm³. All right. Once you get the mole of sodium hydroxide, we need to be able to use this mole of sodium hydroxide to find the mole of HCl. So the 22, it was just a made up number from the graph because we didn't actually plot it accurately. All right. So we just say, let us assume that on the graph where the points meet, it was 22 cm³. All right. So we are using a balanced equation to relate this mole of sodium hydroxide to HCl. So based on the balance equation, the mole ratio between sodium hydroxide and HCl is 1:1. That means any amount of moles of sodium hydroxide that was used, it is also the same amount of moles of HCl. And since we use 0.05 moles of sodium hydroxide, that is how we know that the mole of HCl that was present is also 0.05. And so, once you get the mole of HCl, we already have the volume. So molar concentration is simply the mole divided by the volume. And we get the molar concentration.
Sir?
Yes, go
Sir,
ahead.
what if the mole ratio was a 1:2? How
All
you
right.
do?
No, so when it's 1:2, don't read it as 1:2, as in, all right, so in this case, right? So let me just switch HCl with sulfuric acid, H2SO4. You would have gotten 2 moles of sodium hydroxide to 1 mole of sulfuric acid. In this case, 2 moles of sodium hydroxide to 1 mole of sulfuric acid. However, in the question, you have to look at which one of them you actually have the moles 4. So in this case, you have the mole of sodium hydroxide. So if 2 moles, all right, since as you're asking this, I don't want you to make any mistake tomorrow. So if you get a moderation question, the safest way to do it, all right, just do it like, so 2 moles produce, or 2 moles of NaOH react with 1 mole of sulfuric acid, all right? Therefore, 0.05 would react with X, and you just transpose. And next way you could do it, right? If since has 2 moles of sodium hydroxide is reacting with 1 mole of sulfuric acid, the mole of sodium hydroxide must always be 2 times the amount of sulfuric acid. So all you would have to do is divide it by 2, because the mole of sodium hydroxide must always be 2 times the amount as sulfuric acid. So you have the mole of sodium hydroxide and you want the mole of sulfuric acid. So to go from 2 to 1, right? It means you would have to divide by 2. 2 divided by 2 would give you 1. So going from sodium hydroxide to sulfuric acid, you would divide by 2. However, if the 0.05 mole was for sulfuric acid, then the situation would flip. You would be going from the 1 mole of sulfuric acid to 2 mole of sodium hydroxide, in which case you would have to multiply by 2. All right?
Yes, sir.
Right, so if you have the mole of sodium hydroxide, you would be going from 2 to 1. And for mole ratio, when you're going from large to small, you divide. And if you're going from small to large, you multiply for mole ratio. So if you have the mole of sulfur, if you have the mole of NaOH and you want the mole of sulfuric acid, you are going from large to small, so you would divide by 2. If you have the mole of sulfuric acid and want the mole of sodium hydroxide, you'll be going from the smaller number to the larger number, so you will multiply by it. So you will times it by 2. So it's not just saying it's a 1 to 2 mole ratio, I'm going to times it by 2. Depending on which one you have the moles for, you're going to either multiply or divide. Is that clear?
Thank you, sir.
All right.
Sir, when you write the balance equation, no matter which side you put the H2SO4 and the NaOH.
When you say it matter which side, as in if you put sulfuric acid, then the NaOH.
Yes, sir.
No man, it's all right, because I see products you get. All right, so it no matter.
Okay.
All right, so let me see the 2017 one now.
Sir.
Yes.
Excuse me. How you got the sulfuric acid?
Oh no, man. She was just asking what if it was a 2 to 1 mole ratio. So I took out the 8 scale. So it was just an example.
Oh, I understand.
All right. All right, so 2017, we have a gravimetric calculation. All right, good. So we can do that calculation. Not 2017, this is what, 2018. Someone said they were going to send me a 20.
Sir.
Yes.
For the question C, which is the question before the gravimetric analysis, could you answer that?
There was question C.
C, the one that saying list the appropriate pieces of apparatus.
It's solvent extraction. We don't remember.
Yes, so which?
Right, but solvent extraction is not coming, but if it was coming, you would need A, till this, A, H, So you would use A, H, that's H, and D. But for the gravimetric analysis part, right? All right, so for the 2017 paper, the question 1 or question 2 again, it asks about accuracy and precision. All right, and solvent extraction, but we're not doing solvent extraction. There's also part on gravimetry, so we are going to do the gravimetry part. So it says, it gives a list of apparatus, and we're supposed to choose 2 pieces for gravimetry. Based on your knowledge of gravimetry, tell me some apparatus that we normally use for gravimetric analysis.
Whoa. Buckner funnel.
Suction flash.
Buckner funnel, suction flash, right?
Crucible.
Crucible.
Vacuum
All right, so we have the crucible, we have the Buckner funnel, we have the suction flask. All right, and vacuum pump as well, but they did not put that one here. All right.
Sir, which one are the answer?
So we have the crucible, we have the Buckner
Which
funnel.
which letter?
All right, so B, so for gravimetry, it would be B, F, and E. B, F, and E. So B is the Buckner funnel, F is the crucible, and E is the suction flask. All right.
Use G for gravimetric. G and E.
G, no. All right, so we're going to perform a calculation now pertaining to gravimetry.
So which question is this on the 2017 paper?
All right, so this is 2017, number 2, part D. 2017, question 2, part D. All right, so it says a gravimetric analysis was performed to estimate the percentage of calcium ion in a sample. All right, so an experiment was done. Sorry, this. Right, so an experiment was done to estimate the percentage of calcium ion in a sample. A sample of, right, so 0.496 gram of limestone. So the calcium carbonate was dissolved in acidic solution. Why was it dissolved in acidic solution and not water?
Insoluble in water.
Insoluble in water.
So you have to choose a suitable. So when you're doing gravimetric analysis, if the compound you're analyzing is a solid sample, you have to choose a suitable solvent. And so, because it is insoluble in water, we use acid. All right. Now it says the calcium was then precipitated as hydrated calcium oxalate. So it was precipitated as hydrated calcium oxalate. And the dry precipitate was found, all right, so the precipitate now was found to have a mass of 0.619 gram. So the first one, or the first question, write the equation for the formation of the dry calcium oxalate precipitate. All right, so we want to find the percentage of calcium ion in a sample. We dissolve 0.496 gram of limestone, right? And then the calcium was precipitated as hydrated calcium oxalate. After drying, the dry precipitate weighs 0.619 gram. Now it says write the equation for the formation of the dry calcium oxalate. Are they asking for the precipitation reaction? What do you think they're asking us for? Write the equation for the formation of dry calcium oxalate precipitate. Here it says hydrated calcium oxalate. So if this is the formula for hydrated calcium oxalate, what would be the formula of dry calcium oxalate?
So just the C2O4?
That is correct. That means, so write the equation for the formation of dry calcium oxalate. So we have calcium oxalate. At the end, we have hydrated calcium oxalate. That means we would have to apply heat. And when we apply heat, the water would have been removed. And so we end up with calcium oxalate. All right. So remember, we cannot have water in our precipitate. So after filtration, we have gotten hydrated calcium oxalate, but it has in water of crystallization. So we heat it and we get rid of the water. So this is the equation that we would write, because it did not ask for the precipitation of calcium oxalate. All right, what would have been the precipitation equation? Because this is the equation for the drying process. What would be the equation for the precipitation process? Can anybody tell me?
So would it be reacting your limestone with the acid?
No, that part is just dissolving the calcium carbonate. So just like how you would dissolve sodium chloride in water, right? What is the precipitating reagent here?
Isn't it the water?
No, we didn't use any water here. That is correct somewhere here. But what is the I want to hear the answer. What is the precipitating reagent?
Is it the calcium oxalate?
Not calcium. No, calcium oxalate is the precipitate.
Oh, the calcium.
Mm-hmm.
But
what else? So
the
oxalate
acidic solution.
All right. So the precipitating reagent is the solution that you add to the mixture to form a precipitate.
Not the acid.
So is it like the acid, the KOH or whatever?
All right, let me give you a quick example and then you answer it. If I am analyzing the amount of chloride ions in water, right? And I add a solution of silver nitrate to the sample, I am going to get a precipitate of silver chloride. So my precipitating reagent is silver nitrate, because when I have the silver nitrate, my chloride ion, which I am interested in, is precipitated as silver chloride. So if I am interested in calcium ions, the calcium ions were precipitated as what?
Wasn't
They
it
were
precipitated with the
Calcium carbonate.
oxalate acid?
Hydrated calcium.
They were precipitated as calcium oxalate. So the question we're analyzing, we want to figure out the percentage of calcium ions in a sample of calcium carbonate. So we actually need to get the calcium ions from the carbonate ions. How are we going to do that? We first need to find a suitable solvent. Clearly, it cannot be water because it will not dissolve in water. So we use the acid because we know that if you react carbonate with acid, you are going to get calcium chloride, which is a soluble salt, carbon dioxide and water. So when you react the calcium carbonate with acid, that frees up the calcium ions from the carbonate ion. So now that the calcium ion is free, we need to convert the calcium ion to a precipitate, because for gravimetry, we are going to weigh, so it deals with mass. So after you free up the calcium ions, we need to be able to convert that calcium ion to a precipitate so that we can collect it and weigh it. So the calcium ion that we're analyzing is in the calcium carbonate. So to separate it from the calcium carbonate, we react it with we react it with hydrochloric acid. Good. When you react it with hydrochloric acid, this is what you will have. So in the container, you will have calcium ions, chloride ions. The carbon dioxide, the carbonate would have been broken down into CO2, and that would have escaped. So what we need to do now is convert the calcium ions to a solid form. That is when we add the precipitating reagent. They did not tell you clearly what it was. But remember, the calcium ion, whatever solid form it is in, let's check it out. The calcium ion is now what? Calcium oxalate. That means the precipitating reagent was a solution of what? Oxalic acid. Because where did the oxalate come from? That is your precipitating reagent. It combined with your analyte. So you were interested in the calcium ions. So whichever ion it combines with, that is coming from your precipitating reagent. So if you've got calcium oxalate, that means your calcium ion. So this now is the precipitation reaction. The calcium ions would have combined with the oxalate ion, which is C2O4 2-. And that is how you would have gotten a precipitate of calcium oxalate. All right. So the oxalate is the precipitating reagent. It combines with the calcium ion to give you a precipitate of calcium oxalate. So they could have easily asked you for the precipitation equation and not the drying process, because they don't normally ask for the drying equation. It is normally the precipitation reaction that we are interested in. All right. So let us continue.
Sir.
Yeah.
What's the state symbol on the hydrated calcium oxalate?
It's still solid one, because remember it's a precipitate. So remember in the process, when you add the oxalic acid or any salt, that is contained in the oxalate ion. That is how you get the precipitate. Remember, when you filter it, it is still going to have the water present. That is why you have to dry it to get rid of the water. All right? We're on gravimetric, even though we're going to do calculation. Give me a possible source of error. Not a source of error. Give me a precaution. During the procedure that we just went through, give me a precaution.
Sir, to rinse off the precipitate.
Rinse the precipitate with?
Distilled water.
All right. And why are we rinsing the precipitate?
To remove
contaminants.
All right, to remove contaminants or impurities, right? Good, all right. So let us look at it. It says now, calculate the percentage of calcium in this sample. All right, and we get 4 marks for that. Remember, for gravimetry, the first thing we're going to do is calculate the mass, sorry, not the mass. The first calculation, we are going to calculate the moles of our precipitate. They gave us the mass of the precipitate. This is the formula of your precipitate. So how do we calculate moles? If we have the mass and we want moles, what is the formula?
Mass over R.
In the meantime, somebody just calculate the, all right, let me see if they gave it on the paper. No, they did not. Right, calcium is 40. How much again?
128.
All right. So
Sir, what we're doing now?
We are calculating the percentage of calcium in the sample. So for this form of gravimetry, the calculation are standard. So the first thing we're going to do is calculate the moles of the precipitate, which is calcium oxalate, CaC2O4. So the mass of the precipitate is 0.619 gram. And you said the molar mass was 128 grams per mole. What is the answer?
0.0048.
Please repeat.
4.8 times 10 to negative 3.
0.0048.
0.0048 moles. All right. So the first thing I'm going to do is calculate the mole of the precipitate, which we just did. We don't need this equation. The equation we are interested in is the precipitation equation. So your second step, so after you calculate the mole of the precipitate, you are going to write the precipitation equation, which is what we have here. Calcium combined with oxalate to get calcium oxalate. What we need from this equation is the mole ratio between our analyte, whatever you're interested in, which is the calcium, and the precipitate. So the mole ratio between the calcium ion and calcium oxalate is 1 to 1. So if the mole ratio between calcium oxalate and calcium is 1 to 1, what is the moles of calcium ion?
The same 0.0048.
That is correct. So step 3 now, the mole of calcium ion is equal to 0.0048 moles. So if you have the mole of calcium ion, what can we use? Can we use the mole to find mass?
Yes, sir.
Yes, sir.
So mass is equal to mole times
molar mass.
So 0.0048 times 40 will give us how much?
0.193 grams.
0.193 grams. So the final step now is to calculate percentage. The percentage of calcium, it's the mass of calcium So that's 0.193 divided by the mass of the sample. And the mass of the sample was 0.496 times 100. What is the answer?
38.9.
All right, so we get 39%. All right, and that is how we do it. So, step one, calculate the mole of your precipitate. Write the precipitation reaction, get the mole ratio. Use the mole ratio to find the mole of what you're interested in. When you get the mole, if it was a liquid sample, you would be finding molar concentration. And at this point,
Excuse me, sir. Will you be posting this right after you finish?
Please repeat.
Will you be posting this right after you finish?
Yes, I will.
Okay, sir.
Sir.
Yes.
Sir. So for the percentage Ca2 plus mass, you have that's 0.193 over 0.496.
Oh, 496. Sorry about that. Is it still 39?
But if you're running sir, you'll get 39, but it's 38.91. If you don't run it.
Okay. Whichever you put it, all right. So 39 or yeah. It's gravimetric still. How much I get? 38 point how much?
38.912.
Yeah, 38.91.
38.9%. All right, so
where did the 0.496 come from again?
It's the mass of this sample. So whenever you calculate the percentage, it's the mass of the compound that you calculate over the mass of the sample.
Okay, all right. Thank you.
Yeah, man. All right, let me see what was given for number 5. All right. So number 5, we have a next calculation for number 5. So we're going to do number 5. All right, and it's a next thermometric titration.
Excuse me, sir.
Yes.
Before you move on, what were you saying about if we were given a liquid instead of?
Right. So because it's a solid sample, we're finding percentage composition. A liquid, you would have been finding molar concentration. So where they gave you the mass of the sample, they would have given you a volume for the sample. So let's say 20 mils.
Mommy.
And so
why you
once
kill
you
me sitting there? I'm feel one must done chat by now. Let's say you come up say that 3%.
Right. What was I saying? Not to remember. Oh, yeah. So once you get the mole, the next step would be to calculate molar concentration. And so you would have divided the mole by whatever volume was given in the question. But because it's percentage, after you get the mole, you calculate the mass. All right? So that's the difference right here.
Okay, sir, thank you.
All right. So for this question now, so a student, so it's still 2017 question 5, part B. All right, so for part 1, just send me an email. I'm going to send you a PowerPoint that answers anything to do with uses and properties and so forth. It is in the PowerPoint. All right, so just send me an email and I will send it to you.
Sir, so what email? What's the email?
Somebody just type it in the chat for me, please. That has it. All right, so we need to, it's basically 7, and we need to do some module 1. All right, so this, no, that. So the calculation part of it. A student standardized an unknown solution of acid H2A. So let me go to the board. Oh, we can make the mic now. Thanks. All right, so yes, so a student standardized an unknown solution of acid H2A by adding successive 5 cm cube portions of acid to 25 cm cube of sodium hydrogen carbonate. All right, so H2A is the acid, and we have sodium hydrogen carbonate, and they gave us the concentration.
Sir, what year are you doing?
2017, question number 5, part B, no, part C. All right. So they gave us the concentration, which is 0.25. This is thermometric titration again. All right. So I'm just going through the question. So we have a solution, unknown solution of an acid H2A. And we're titrating it with sodium hydrogen carbonate, and we're adding 5 cm cube portions of sodium hydrogen carbonate to the acid. All right. And the temperature is taken after each addition. The data was collected and we plot a graph. So the calculations now. So the first calculation, it says calculate the number of moles of carbonate used. So remember, we were adding the carbonate to the acid. So when we plot the graph, we are plotting the temperature versus the volume of the carbonate. Now, and they plotted the graph for us, right? And they plotted it as expected, with it as that shape, right? And this point, when you look on the graph, the line coming down, it matches with 20 cm cube. All right, and remember, the only thing we need the graph for is to get the volume of acid used or the base. So in this case, it's the volume of sodium hydrogen carbonate. Where the line intersect, you just draw a line down to the x-axis. And on the graph for 2017, if you look, it will match up with 20 cm cube. So the volume of sodium carbonate used is 20 cm cube. So the concentration was 0.25. From the graph, the volume is 20. So we have concentration and we have the volume. So we can go ahead and calculate the number of moles.
Sir.
Yes.
Sir, for the question says that the acid is what you're trying to get, not the sodium hydrogen carbonate.
You're trying to get the acid, sir, so
So
you
the
would
20
use 25 cm cube for the question, right?
Yes, sir. So the sodium hydrogen carbonate is 25 cm cube and the acid is a 20 cm cube.
Oh, we add successive 5 cm cube of the acid.
Yes, sir. 225.
Oh, yes. Thank you for that. All right. So the acid, also here, this would have been the acid. So volume is 20 cm cube. All right. And this is 25. All right, so mole, we know that mole is concentration times volume. The concentration is 0.25 and the volume in dm³ would be 0.025. What's the answer for that?
0.00625 moles.
All right, so 0.00625 moles, all right. And then it says calculate the number of moles of acid reacted. How would we get the mole of acid?
You would write your equation, sir.
Is correct. So H2A reacts with sodium hydrogen carbonate. Let me see who can tell me what would we get over here. Let me see if I can figure it out. I'll give you a few seconds.
Sir, you will get Na2A plus CO2 plus H2.
Na2X plus CO2 plus H2O.
Plus H2O.
Tell me why you say Na2X.
Sir, because in the acid you have the two right there. Yes, sir, right fingers.
That is correct. So the charge on hydrogen is H plus. So if you use two hydrogen ions, it means that the charge on the acid is 2 minus. Because if you write the formula, 2 would come here, right? That's a 1. So more than likely your acid is sulfuric acid. So it's a dibasic acid. So sodium is also, just like hydrogen, has a positive charge. So therefore, if you need 2 hydrogens, you're also going to need 2 sodium. So Na2X is correct. All right. So after we do that, is the equation balanced?
No, sir.
What do we need?
You need 2 sodiums.
That is correct. So we need 2 sodium. Hold on. If it's not X, it's A, Na2A. Sorry.
Yes, sir. I said A.
Yeah. No man, I add X here, so I was just correcting it. Is it balanced now?
Oh, sir, I put in front of the H2O.
A.
2 in front of the H2O. All right.
There's.
Don't you also
Why
need
would you
in
put
front of
2 in
carbon
front of the
dioxide?
H2O, sir? I don't think you need to at all.
You have 2 hydrogens here.
Yeah.
And you
Exactly.
have 2 here. So that's
so
4.
You don't need it.
No, that is what we needed 2.
Oh,
You have 2 in hydrogen carbonate and 2 in H2A. So
Sir,
that's
you
4.
need to add 2 at the carbon dioxide.
And yes, 2 at the carbon dioxide, that is correct. So because you put 2 in front, remember when you put 2 in front, it goes for everything in the compound. So 2 sodium, 2 hydrogen, 2 carbon, and 6 oxygen. Now for oxygen, 2 2s 4, 2 1s 2, so 4 and 2, that is 6. And don't forget our state symbol. So aqueous, aqueous, liquid, gas, aqueous. So 1 mole of the acid reacts with 2 moles of the carbonate. So what is the mole of our acid? Are we going to multiply by 2 or divide by 2?
Divide by 2.
Try to multiply.
All right, so we have the moles for what? Hydrogen carbonate. So we have the mole for hydrogen carbonate. And we need.
So that is from larger to smaller, so you multiply.
For mole ratio, from larger.
We're going to divide, right, sir?
Divide by 2, right? So for mole ratio,
all right.
Yeah, from large to small, you divide. So it is
Sir, the
going to be
easiest method I use is for the unknown, write X under the unknown.
Right, so whichever is easier for you, yes, just use it because there is more than one way, all right? So 0.00625 divided by 2, how much would we get?
0.00.
003125.
0.00
3125.
31, all right, 313, all right? So let us just look at what happened again, right? They gave us the concentration of the sodium carbonate, of the sodium hydrogen carbonate, and the volume. They asked us to calculate the moles of it. So we know that the mole is the concentration times the volume, and we get that. They did not ask us to write a balanced equation. All they did was ask us to calculate the moles of the acid. But we know that the only way to get the mole of the acid
is to know the ratio.
This equation, and then using the mole ratio to get the mole of the acid. So we write the balance equation. We saw that the mole ratio was 1 to 2, but we had the moles of sodium carbonate. So to get the mole of the acid, we divide by 2. And that is how we get the mole of the acid.
So now we're going to divide by the concentration.
By the volume.
No, the volume, yeah, to get the concentration, sorry.
So the mole of H2A is that. And then they ask for the concentration of the acid. All right. Is anybody writing or can hear this now?
Excuse me, sir. Someone is asking that you re-explain this question.
Re-explain the quick question. All right, so it's a thermometric titration, right? So we add the acid, sorry, which one did we add to which? Let me check. We add the acid to the burette, right? Sorry, we add the acid to the container with the sodium carbonate. And remember, so we add 5 cm cube each time. And remember, every time we add, we record the temperature. At the end of the experiment, we plot a graph of temperature versus volume. We plot a graph of temperature versus volume of the acid. And remember, where the two lines intersect, we're going to draw a line down to the x-axis so that we can get the volume of whatever was in the burette. The acid was in the burette. And when the two lines are intersected, and I draw a line down to the x-axis, it was pointing to 20 cm cube. So we got the volume of acid from the graph. Then the first question asks us to find the mole of sodium carbonate, sodium hydrogen carbonate. 2017, number 5, part C. So the first question asks us to calculate the moles of sodium hydrogen carbonate. To do that, we multiply the concentration by the volume, both of which were given in the question, and we get the moles. The second question asks us to calculate the mole of the acid. To get the mole of the acid, we have to use mole ratio. To use mole ratio, we need a balanced equation. That is why we write the balance equation, then the mole ratio. And we use the mole ratio to get the mole of the acid. Once we get the mole of the acid, we simply divide it by the volume and we get concentration. So now we're going to calculate the concentration of the acid. All right, so yeah, the concentration.
Sorry, you said 1 cm cube equal to 1000 dm cube, right?
No, 1000 cm cube is 1 dm cube.
Okay.
Yeah. So the mole was 0.001313 divided by, please mute the mic. Volume is 0.02 DMQ.
Zero. Yeah.
And what's the
Sir, we
answer?
get 0.16 moles per dm cube.
Alright, 0.16 moles per DMQ. Alright. Now, that's the end of the question, but after they ask for molar concentration, if they want, they can ask you for mass concentration. Now, in a titration, so we know that mass
Sir, you
concentration.
just
You
Sir,
wanted
me
the
not
answer
see that.
for number one?
What is the concentration of the acid? You just do it.
Yes, it's here. This is the
Can you
concentration.
repeat it, please?
So concentration is mole over volume. Down here, we got the mole of the acid. Remember, from the graph, we said the volume was 20 cm cube. The unit for concentration is moles per dm cube. So convert the 20 cm cube to dm cube. So 20 divided by 1,000 is 0.02. 1 dm cube is equal to 1,000 cm cube. All right. So all I did was convert the 20 cm cube to dm cube. All right.
Sir?
Okay, sir.
Yeah.
In a reaction like this, would you need to pay keen attention to the amount of significant figures you continue using?
You can work with 3 if you want. No, the thing, no, you see with this one, you see the more zeros I have, the Z, you want to use as much actual numbers that will affect the answer. So what you can do is work with standard form. So you could just say 3.13 times 10 to the minus 3.
Right, right, sir.
All right, we need to do some manual one. It's after 7.
Sir.
Yes.
Sir, look at question D. Could you give me an answer for that? The part D of that question.
I'm going to post them in the, but when I'm uploading the video, I'm going to write the answers in the description for the written ones. All right. So just check the description.
Excuse me, sir. Before you start Thermometric and titration, you were speaking about a type. You were saying that there's thermometric, potential, differential.
Potentiometric and conductiometric, something like that. I don't remember the exact name.
And
but,
you were explaining to an extent, and then somebody stopped you. I was wondering if you could explain.
So with those two, right? With those two, just like with thermometric, you will get, if it comes, it's a graph. So you will plot a graph, and just like with thermometric, you will have to extrapolate the reading. All right, and it's not a straight line graph. All right. So they will look like this. All right, and you extrapolate the reading. But they haven't come because they put it in
Both of the graphs should look like that then.
Right, so for thermometric, it looks like this, goes up and come down. The other two, so it's still 2. You will have to get 2 lines and you read it from where they intersect. All right? But I haven't seen them ask anything about it because if it's either acid-base, redox, or thermometric when it comes to graph.
Excuse me, sir. What
Yes.
would we do if they ask for mass concentration?
Oh, yeah, for mass concentration, even though, so mass concentration is mass over volume. But when you do a titration and you calculate the molar concentration to get the mass concentration, you will simply multiply the molar concentration times the molar mass of the compound. All right. Let us just say that the acid is sulfuric acid, right? So the concentration is 0.16.
Sorry, that's the molar concentration times what?
Times the molar mass. So it would be 0.16 times 98 gram per mole. So just remember I said that, let us just say that H2A is sulfuric acid. Then the molar mass would have been 98 gram per mole. Mole cancel mole. 0.16 times 98 is how much?
15.68.
15.68
grams.
All right, grams per dm cube. All right, so if you are doing a titration and they ask you for mass concentration, just calculate just multiply the molar concentration that you get by the molar mass of the compound. All right.
So which of the compound?
So in this case, it was H2A, but we don't know what A is. So I was saying, let us just assume that H2A is sulfuric acid. All right. The molar mass for sulfuric acid is 98. This is not a part of the question, you know. I was just reminding you that if they ask you for mass concentration, you just multiply the molar concentration by the molar mass of the compound. All right. All right, so yeah, module 1. Go to question number 1 of 2017.
So for
yes.
For the titration questions, those are the only things they could ask for.
Yeah, or let me see. In terms of the calculation, they
Yeah.
can ask about uses of titration. They might ask about for thermometric, they can ask about the procedure. That is why I went through it as well.
Okay, thank you.
Yeah, ma'am.
Sorry, that's where you add 5, like for example, 5 centimeters of the acid to the base, right?
And remember, you don't use a conical flask. You use a styrofoam cup because you don't want, because you want to minimize heat loss. Remember to send me an email. I have the information with that in a PowerPoint, so I will just send it to you. So in terms of uses of gravimetric, properties of or characteristics of primary standard, all those little stuff, apart from the calculation, I put them in a PowerPoint. So just send me an email, all right? Because we need to get to module 1 and practice some question again. All right, so on 2017, no, as in send, no, don't give me your email. Send it to my email address. Someone just send my email in the chat again, and you just send it to it.
I'm sorry, what number the 2017 paper again, sir?
Is it real chemistry at 90? Is it real chemistry 92 at gmail.com?
No. It's real.chemist 92 at gmail.com. All right, real.chemist 92 at gmail.com.
Yes, sir. So I was asking which number question was it again?
27. What that I'm going to work now?
Yes, sir.
2017 question number 1.
Okay, sir.
Right. It says state 3 properties of a homologous series. So homologous series, the compounds, they have the same general formula.
Same functional group.
Same functional group.
Similar chemical properties.
Wonderful. And they differ by
Sorry,
success.
could you repeat that? I wasn't hearing them.
So properties of a homologous series, so the compounds, they have the same functional group, they have the same general formula, they have similar chemical properties.
And they differ from a CH2 group.
They differ by successive CH2 groups. And their physical properties, the physical properties increase as the molar mass increase. All right, so here we have a combustion analysis question. So it says an analysis of 1 gram of compound A, an analysis of 1 gram of compound A. So we have 1 gram of compound A. One gram of compound A, and it contains carbon, hydrogen, and oxygen. All right, so it contains carbon, hydrogen, and oxygen. All right, so after the combustion, it was found that it had 0.40 gram of carbon, and 0.54 gram of oxygen. All right, and it has a molecular mass of 60. All right. Before I work it, I'm going to give you 3 minutes. All right, just 3 minutes, and see if you can figure out the empirical and molecular formula. Bear in mind that it contains carbon, hydrogen, and oxygen. 1 gram of the compound, and they gave you the mass for carbon and oxygen. All right, so I'm going to give you 3 minutes, and then work it. Any answers?
Yes, sir. Empirical formula CH2O and molecular formula C2H4O2.
Repeat that. The empirical formula.
Yes, CH2O.
Alright.
Yeah, and for the molecular formula C2H4O2.
C2H4O2.
Yes, sir.
Alright. Let's see if we have the next one for you.
Sorry, you're gonna work out those?
Hang on, I'm going to work it now. All right, so it says it contains carbon, hydrogen, and oxygen. All right, we know the mass of carbon is 0.5, no, the mass of carbon is 0.40, and oxygen is 0.54. How do we get the mass of hydrogen?
I add the mass of carbon and the mass of oxygen and subtract it from the total mass.
And I get 0.6 or 0.06.
0.06.
0.06.
0.06.
So 0.06.
Sir, how you get it, sir?
So they gave you the mass of carbon and oxygen. So you add them up and subtract it from 1 gram. So the sample have been carbon, hydrogen, and oxygen. And you have 1 gram of this sample. And they gave, they told you that it have been 0.4 gram of carbon and 0.54 gram of oxygen. That means whatever is remaining is hydrogen. So you add up the mass of carbon and oxygen, whatever your answer you get, you subtract it from the 1 gram of the sample. And that is how we get 0.06.
Okay, thank you.
Yeah. Right, so the first thing we're going to do is calculate moles. So mole is equal to mass over molar mass. So 0.4 over 12, 0.06 over 1, 0.54 divided by 16. How much you get when you divide it by 12?
0.03.
0.03. All right, this is 0.06. And how much you get for this one?
0.03.
170.
0.0 how much?
3.
All right. All right, so we divide by the smallest number, but in this case, it's 0.03. So this divided by that is 1, this is 2, and this is 1. So you are correct. The empirical formula is CH. The empirical formula is CH2O. So to get the molecular formula now, what you are going to do is find N. And N is the molar mass divided by the empirical formula mass. And that is equal to 60. Let us add up this. 12 and 2 is 14. 14 and 16.
30.
That is 30. So the answer is 2. Whatever N is, you are going to multiply the empirical formula by it. So N is 2. And so 2 times 1 carbon, that's 2 carbons. 2 times 2 hydrogen, that's 4 hydrogen. 2 times 1 oxygen, that's 2 oxygen. Yes, so that is how you would calculate it. All right, there's one I want to work. Though I don't know. Let me see if I have it. But in the meantime, let's work on next question.
Wait, sir.
Yeah.
You wrote that said of 60.
Mm-hmm.
Oh, okay, thank you.
All right. Yeah, come on. Oh, so what is compound A? It says write the general formula of the homologous series of which compound A belongs.
So that's acid.
What are you doing? All right, so let us see. It's a carboxylic acid, 2 carbons, double bond O,
Sorry, is it,
H.
Is ethanoic acid, sir.
sorry, is it ethanoic acid?
All right. C2H4O2. So which homologous series does it belong to?
Carboxylic acid.
All right. And draw the structural formula of the chloro substituted compound of A. All you have to do is replace one of these compounds with hydrogen. Substitute one of these hydrogen with chlorine.
What question is that?
This is still number 1. We're still on number 1. All right, let's just look for some questions on alkenes and alkenes. All right, let me go back to.
Mr. Here.
Yeah. Yes.
So, yeah, good evening. What time class finishing today?
Well, honestly, I'm tired, but so I'm gonna try go to 8 because.
Some realize.
All right, so all right, let me work some reactions of alkanes and alkenes. No, I want to do some isomers first. So let us just look back at the difference. So what are the 2 categories of isomers?
Structural and
Structural
sterile.
and
Right, sterile isomers. Under structural isomerism, we have 3 types. What are the 3 types?
Functional.
Position, function.
All right, so chain, positional, functional, right? So I'm going to put some compounds on the board and they are going to classify them as which type of isomer. All right, so this is compound 1. Try about the blue marker.
So which question is this?
This is from PDF. It's an old past paper question. So probably from anywhere from 2000 to 2006. But I'm not sure of the exact year. This is compound 2. That's compound 3. This is compound 4. And this is compound 5. So your job now, all right? So we have 5 compounds on the board. Which of the compounds exhibit position isomerism? Which of these compounds exhibit position isomerism? And remember, you cannot pick out one compound because if it's isomerism, it has to be at least 2. Right?
I also 1 and 4.
Iron
I said
Ivy.
sir, 1 and 4.
Right.
Yes,
Because,
sir.
right, it's the same compound. The only thing that is different is the position of the chlorine group. All right, good. Which one shows chain isomerism?
2 and 3.
1, 3.
1, 3, right. Same molecular formula, but the arrangement of the carbon atom is different. So good. All right, then it says, from compounds 1 to 4, copy the one that possesses a chiral carbon atom and identify it with an asterisk. So which of these compounds have a chiral carbon?
5.
All right, that is correct. I am going to label the carbon atoms. All right, so this is carbon 1, 2, 3, and 4. Which of them, carbons 1, 2, 3, or 4?
3.
3.
3.
Sure, no 4.
3.
3 is correct. Is there any?
Yeah, I don't hear the question.
Carbon
All right,
4.
so the question is, which of these compounds has a chiral carbon? And the question and the answer is question, sorry.
Carbon.
The answer is
Carbon
number 5.
4.
Sir, can you explain why?
All right, no problem. All right, so for a chiral carbon is a carbon atom with 4 different groups attached. Simply, let me just do this. So carbon, fluorine, OH, H, CH3. All right. So this carbon atom, it has 4 different things attached to it. So it is chiral. That is what it means, right?
Yeah.
Now, however, let me just point out, right? It don't have to be as simple as this, where a hydrogen here, a fluorine here. 4 different groups. So let me just show you something. CH2, CH2OH. You see, all of this is a group. So when you're looking for a chiral, carbon, you're going to identify each carbon, right? You see, whatever is above it, that is a group. Whatever is to the left of it, that is a group. Whatever is below it, that is a group. Whatever is to the right of it, that is a group. So if you look at carbon number 1, 3 hydrogens are attached to it, so it cannot be chiral. It must have 4 different groups. If you look at carbon 2, it has 2 hydrogens attached to it. If you look at carbon number 3, it has a hydrogen attached to it.
An ethyl group to the left.
Exactly. Everything, so remember, everything to the left of it is a group. So all of this here, that is a group.
Then hydroxyl group below.
The right hydroxyl group.
Carboxylic group.
Right. So it's not like we're just looking for the atom that is directly attached to it. Everything to the left, everything to the right, that is a group. So we have ethyl group, carboxyl group, hydrogen, and OH. So 4 different groups. That is why this is a chiral carbon. For carbon 4, once a carbon has a double bond, it cannot be a chiral carbon. Because if there's a double bond, only 3 groups are going to be attached to it. So this one could not be chiral, because only 1, 2, 3 groups could be attached to it. Right? So it says, take the type of isomerism exhibited by this compound. So what type of isomerism is exhibited by this compound?
Optical.
Optical, that is correct. And then it asks for the chemical name of this compound. All right, let's say you have carboxylic acid and OH group. The OH group becomes a substituent group. When OH is a substituent group, it is called hydroxy. So we have 1, 2, 3, 4 carbons, so that is butanoic acid. And the OH is a carbon 2 because they count from the end closest to the functional group. So it's an hydroxy group and carbon 2. So it is 2
hydroxybutanoic acid.
2 hydroxy butanoic acid. All right.
I can go over the naming again.
All right. So we have 2 functional groups present, the carboxylic group and the OH group. But the carboxylic group, it gets the preference in terms of the parent name. So you are going to name it like a carboxylic acid. So we're going to count how much carbon atoms is present. So we have 1, 2, 3, 4 carbon atoms. So so when it's 4, it's but. So it's butanoic acid. The OH group is a substituent, and it is on carbon 2 because they are counting from this end, the end with the carboxyl group. So carbon 1, carbon 2. So the hydroxy group is on carbon 2. So it is 2 hydroxy butanoic acid. All right. Right, let's do some reactions of alkenes.
Sir?
Yeah.
Oh, what? The chat is asking why is the carboxylic group favored?
It's just the rules, all right? So when you have carboxyl group, it gets the preference. All right, so
Sir, a question.
Yeah. Go ahead.
So is it is it because it has something to do with the delocalized election?
No, man, it's just naming compounds, you know, so they choose what gets the priority. So the best according to Ayubak, right, when you have OH, because they have to have a system for naming them. So when you have carboxyl group and OH group, the carboxyl group gets the priority. All right, your background is a bit loud, so I'm going to mute the mic, all right? All right, cool. All right, so before we close, let's do some reactions of alkenes.
Sir,
yes.
So what compound did you get for the something? Because my wife, I logged out accidentally.
Which question exactly?
The one you just did, the question, weren't you doing 2017 question 1?
Oh, it's
did you get acetic acid? Was it acetic acid?
Right, or ethanoic acid. Put ethanoic acid. But it's the same thing, but acetic acid is the common name. All right, so this I'm working, I don't remember which year this come from. I think it was 2011, but I'm not sure. All right, so here we have an alkene. Put this. Let me see if I find a marker that is working. No, give me a second.
Sure.
Just a second. Yes, go ahead.
So when you finish, can you do 2015 question 1 II?
2015. I'll see if I find it. All right. All right, so we have an alkene on the board. So C3H. C3 double bond CH H. All right, so the question is, give the structural formula for the reaction of A. So first with aqueous bromine. So all they want is the structural formula for the compound formed when you react compound A with aqueous bromine. When you react an alkene with aqueous bromine, what are we adding to the alkene?
Is it producing a bromohydrogen? Oh, wait.
OH and Br.
Sorry, isn't
Right.
Come on.
All right, you're correct. We're adding OH and
bromine.
So for this, this is aqueous bromine. Right. You get your bromohydrogen, Br and OH. The next one says when we add liquid bromine. So this is aqueous bromine. How would it look if we add liquid bromine?
A dibromoalkane.
Alright. So we would have a Br on both of the carbon atoms. So when it's liquid bromine, you get a dihalide, so 2 Br atoms. But when it's aqueous bromine, or if they say bromine water, you add a Br and the OH. The next one now says cold potassium permanganate. Cold.
You're from a 1,2 dial. So
that is correct. All right. So it will be CH3, OH, OH. All right. So you just add 2 OH group. And then the next one says hot potassium permanganate. Now I'm just going to use this example to explain what happens with hot potassium permanganate. All right.
Excuse me, sir. What
Yes.
year is this?
I think it's 20. I'm not certain.
Sir,
I just cut some paper and put it in a PDF file. So I'm not sure which year.
So if they were given any other halogens, it would be the same thing.
Yes, any halogen. That is correct. All right.
So these are something for me. HBr. Sorry, Br2 aqueous is bromine water, right?
Right.
So what's HBr?
Hydrogen bromide. So let me just do the double bond portion. The Br will go on this carbon, and the hydrogen of the HBr will go on the carbon that already has more hydrogen.
Yes.
So it will go on this carbon. All right?
Sir?
Yes.
With the hot acidified potassium permanganate, they're saying that it can either turn into like a carboxylic acid ketone aldehyde or a carbon dioxide and
Right.
I think water.
That is what I'm going to explain when I get each.
Oh, okay, sir. Thank you.
All right. All right, so when you react it with hot potassium per manganate, just a second, let me just, somebody's mic is on. All right, so when it's hot potassium per manganate, the double bond is going to be cleaved, right? So wherever the double bond is, just separate the compound. So this carbon here, I want you to convert it to C double bond O. And this other carbon of the double bond, do the same thing. C double bond O. All right? So just split the double bond. We're not adding things to it, we are breaking it apart. All right? Convert it to C double bond O, both of the carbon atoms. And then you are going to put whatever was there, you put it back. So we have a CH3 here, we put it back. We have a CH3 here, we put it back. All right? Ketone, the functional group of ketone is C double bond O with a C on either ends. So if you look, you have C double bond O with carbon atoms attached to it, 2 carbon atoms attached to it. So that is a ketone. In oxidation of alkenes, if you get a ketone, that is the final product. So this is your final product for this portion of the alkene. So the ketone will be your final product. This, however, on the other hand, all right, when you get an aldehyde, they are going to go to a carboxylic acid and stop at a carboxylic acid, except for this. You see a carbon at the end, so the one with 2 hydrogen, that carbon is going to give you methanoic acid. And that is going to be broken down into carbon dioxide and water. So just make a little note. If the carbon atom has 2 hydrogens on it, you are supposed to get carbon dioxide and water. All right? So this would go to methanoic acid and then carbon dioxide and water. All right? So this compound here, it would have gone to give you methanoic acid, HOH, right? Methanoic acid, which would then further give you CO2 and water. All you need to write is the carbon dioxide and water. You don't need to write the aldehyde, then the carboxylic acid, then carbon dioxide and water. All right?
So excuse me, sir. So you're showing me what would happen when you react the hot potassium permanganate with
Hot KMnO4 acidified. All right. So I'm
the
saying
alkene, right?
right. So if the carbon, once the carbon has on 2 hydrogen, and the only time it will have 2 hydrogen is if the double bond is at the end. You get carbon dioxide and water. All right. So the products here, once you spot 2 hydrogens, just know you should get carbon dioxide and water. All right. So it's ketone, carbon dioxide, and water. So as long as the carbon of the double bond has 2 hydrogens attached, you will get carbon dioxide and water. All right. And the reason for that, you would have gotten an aldehyde, but the aldehyde has 1 carbon, and it would have been converted to methanoic acid. All right. Which will then give you carbon dioxide and water. I am going to change the structure of the alkene to show you what would happen if you get an aldehyde in which the carbon has 1 hydrogen and not 2. Yes, you need to know it. All right, but it's not hard. Just remember, if you have 2 hydrogens on it, you must get carbon dioxide and water.
No matter where the hydrogen, yes, sir.
Repeat?
It no matter where the hydrogen, it's 1 or 2.
1 or 2, but because you're paying attention to the double bond, you will not, the only time you will have 2 hydrogen is when it is at the end. All right?
Okay.
So let me show
So
you
you have
let me show you an example.
they have to show the previous working before you get the carbon dioxide and the water?
No previous working. I was just explaining, all right? So you just put carbon dioxide and water.
Okay, so
Okay,
that's
thanks.
when we are at the hot potassium permanganate with the alkene, right? You get the ketone plus the carbon dioxide plus water, right?
All right. So it's what you get is based on the structure of the alkene. So remember, all we did was cleave the double bond. Each carbon of the double bond, we convert it to C double bond O. Everything else remain on it. When you observe this structure, this is a ketone. Nothing else will happen to the ketone. It will just stay as a ketone. For this one, C double bond O, H, H. When you get an aldehyde, it will not stay as an aldehyde. Ketones stay as ketone. Aldehydes do not stay as aldehydes. They get converted to carboxylic acid. So when you get an aldehyde, the final product would have been a carboxylic acid. But when the carbon has 2 hydrogens on it, so a single carbon with 2 hydrogens, you are going to get methanoic acid. And that will break down to give you carbon dioxide and water. So that is what I'm saying. If you get a carbon, right? If the carbon of the double bond has 2 hydrogens on it, then their final product is carbon dioxide and water. So based on this structure, it's a ketone, so it stays as a ketone. Now I'm going to adjust the structure. Let's go again. All right, let me take out this one. I'm going to change this to a hydrogen as well. So again, we would cleave the double bond, right? And each carbon of the double bond, we are going to write C double bond O. And then you put back whatever was present. So for this carbon, it had on hydrogen, and it had on CH3. For this carbon, it had on hydrogen, and it had on CH3. The functional group for the aldehyde is C double bond O, H, and however amount of Cl. So which functional group do we have here? Is it aldehyde or ketone?
Sure, that's an aldehyde.
Right.
Aldehyde.
Right. So C double bond OH, that's the, where does the O come from? It's oxidized. All right. Well, tomorrow is the exam, so just kind of catch what you should do. All right. When you cut the double bond, just put C double bond O for each of them. In this case, we have aldehydes. When you get an aldehyde, that is not the final product. It is going to be further oxidized to a carboxylic acid. All you're going to do, where have the H attached to the carbon, just change it to an OH. All right, so this H, it becomes OH. And that's how you get your carboxylic acid. And the same goes for this. You would also get a next carboxylic acid. All right. So once you get an aldehyde, as long as it has more than 1 carbon, it will be converted to a carboxylic acid. Now, if you want to arrange the aldehyde like this, there is nothing wrong. They are all attached to the same carbon atom. So if you want to arrange the carboxylic acid like you're accustomed to, then there's no problem either. Because they are still connected to the same carbon atom. All right? So look, your carbon atom of the double bond, if it has one hydrogen, you will get an aldehyde, which will go to the carboxylic acid. Once it has one hydrogen, you will get aldehyde. And you must further convert it to a carboxylic acid. If the carbon of the double bond, if the carbon of the double bond, if it has no hydrogen, so look at it in this case. If it has no hydrogen, that is when you get the ketone, because at this point, you would have gotten C, double bond O, CH3, CH3. All right, so you can make a note. No hydrogen, you will get a ketone and it stops there. One hydrogen, you get an aldehyde, you convert it to a carboxylic acid. So if you do this on the exam, that is not the final product. This is the final product. All right? And when it has two hydrogens, you must get carbon dioxide and water. Understood?
Yes, sir.
Yes, sir.
Yes, sir.
So it says state whether compound A exhibits geometric isomerism. So let me have a compound A, and we're going to see if it exhibits geometric isomerism.
I'm sure that's cis and trans, right?
Right. Before I draw compound A, just remember, in order for you to get cis trans, so let me draw two compounds. All right. These are the two compounds. Each carbon atom of your double bond must have a group in common. If they don't have anything in common, you cannot have cis trans. I'm going to show you why. So CH3, CH3, F, Cl. For cis and trans, it's a stereoisomers. It means that the atoms are bonded together in the same exact way. They just differ in their arrangement in space. So the reason why we need two atoms in common are two groups of atoms. So the atoms in common here are the group in common is the methyl group. Now, the double bond restricts rotation. So at no point in time can the CH3 flip and come up here. So in the next compound, this can happen. Remember, the double bond prevents rotation. So these two compounds are not the same in terms of their spatial arrangement. At no point in time will this methyl group come over here so that it looks like this. So when the methyl groups are across from each other, that is how you get trans. And when they are on the same side of the double bond, that is how you get cis. Now, let me try and put it here. C, double bond C, CH3, CH3, Cl, and F. If you have the two methyl groups on the same carbon atom, can we get them across from each other? Can we get it like this? If it is attached to the same carbon atom, can we get it looking like this?
No, sir.
No,
sir.
No, sir.
Okay.
No, sir.
Right. So if the groups, so the criteria, the both of the carbon atoms must have a group in common. And the reason for that, for cis trans, when it's the groups must be on the same side, it's cis. When they are across from each other, it's trans. So if they don't have any group in common, right? Then what are we going to compare? We don't have anything to compare, right? To say they're on the same side or opposite sides. And the next thing, if the group is on the same carbon atom, then we still cannot get cis or trans. Because for cis, they must be on the same side of the double bond. And for trans, they must be across from each other. All right? So with this said, let me put my compound A, and you tell me if it exhibits cis-trans isomerism.
Sir, this is the same thing, like trans is the same thing as E isomer and cis is the same thing as Z isomer? Z?
The easy scheme?
Yes, sir.
Yeah. But it's when you go level one, they really got both, they really talk about easy, the easy scheme. Yes, about 30 minutes after class ends, it will be uploaded.
Sir, this is an example of geometric isomerism, right?
Right, so geometric is also called cis-trans. Right? So let me put my compound A on the board. So that is compound A. Does it show cis-trans isomerism?
No, sir.
No.
No.
None.
No, sir.
No, sir. No, sir. Carbon.
All right, so C, if you're asked to draw cis-trans, so if they give you the compound like this, right? When you join cis-trans, you draw the carbon to carbon double bond, and then you do this, all right? So you set it like that. So we have H there, H here, CH3 here, CH3 here. Remember the criteria we said that what? Both carbon atoms of the double bond must have a group in common, right? And if we look, does the carbon atoms have a group in common?
No, sir.
No, exactly. So if they have no group in common, we cannot have cis or trans. What if the hydrogen was on this side and the methyl group was on this side? Could we get geometric isomerism?
Yes, sir.
Yes,
Yes, sir.
Because
That would be cis isomerism.
now we have group in common, we can have them on the same side or we can have them on opposite sides. You know? So, because the two methyl groups are on the same carbon and the two hydrogens are on the same carbon, at no point in time they can be on the same side of the double bond or across from each other. So it couldn't be cis. All right, so I'm going to close here, all right, and upload it. All right, so
Sir,
yeah.
sir, do you teach math?
Just come on by you.
Okay, thank you, sir. You're an excellent
Right.
teacher, sir. You should teach math.
Thanks. Have a good night.
Thank you, sir.
Yeah, man.
Thanks,
Thank you, sir. Thanks.
All right.
God have a
Hey,
blessing,
sorry,
sir.
Bio Unit
Thank you,
2?
sir.
Sir,
Yeah.
make sure you
Sir,
post it right
much
after.
appreciated.
Thanks.
Sir, bio again, sir. Bio again, sir.
Our number.
Sir, how about pure maths?
Let's come on bio.
Yeah, but bio is
20.
Yeah,
The
yes,
30
sir.
and the 20.
The 20th.
13th and the 20th, sir.
We'll arrange a class for that, all right?
Paper 2 is a 20. You
All
get a
right.
link.
Sir, pure math, huh?
So check about 8:30, all right?
Sir, how would you get a link for bio?
Similar how you get this one. I don't know how you get it, but similar how you get it.
Okay,
On
sir,
YouTube.
in measurement.
On YouTube. Post
If you email me, I'm going to send you the PowerPoint at, it's now 8:08. I will start replying to the emails at 9 o'clock. All right? So you can look for the PowerPoint at 9 o'clock. All right? And all the best tomorrow.
Thanks, sir.
Thank you, sir.
Thanks, sir. Yes, so I'm going to close it now. So have a good night. All right?
Good night, sir.
Good night, sir.
Thank you, sir.
Let me stop the recording.
Thanks.
Don't forget about the recording.
Thanks, sir.